This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. So we can now look at the idea of compactness. A lot of students kind of struggle to understand compactness. Later on, we actually give an equivalent definition to it, which will make it a lot easier to understand, but that'll only hold in RD. This is the more general definition of compactness, which can be used across non-real sets. So it's a little annoying to look at if you're just looking at real real analysis, because it ends up being equivalent to already familiar concepts. So we say that an open cover of any set in RD is a collection of open sets. So here it's U sub I to show that each UI is one of the sets. And here I have I, an element of large I, capital I. This is common notation you use. It just means that I is an element of this big I, where big I is some indexing set. So that could be a finite amount of numbers, it could be 1, 2, 3. It could be all the odd numbers, it could be the natural numbers. Just any set here, potentially infinite, which is used to index each of these UI. So it gives us some ways to make sure that we've listed them all out. So each of these UIs is open in RD, and when we take the union over every I in the indexing set, that X will be contained in the union of all these sets. So if X is just this blob here, we can take U1, U2, U3, and U4. They all overlap here. And in their union, so they're all open in RD, and X is contained in their union. Therefore, this is an open cover of X. This is hopefully an easy enough definition. You basically just take any set in RD, and if you can cover it in open sets, hence open cover, then that's exactly what it is. But this is a much trickier definition. X is compact if every open cover of X has a finite subcover. So a finite subcover just means that if we look at the open cover, we can take finitely many of the open sets in that open cover, and that will form a new open cover of X. So that just means that this I here, there has to be some subset of this capital I where if we take just the sets which are indexed in that subset, in that finite subset, then that would still form an opening cover of our set X. So that's kind of the definition of compactness. It should align with your regular kind of use of the word, in that a set that is not sort of very well contained, you won't be able to do this sort of operation where you take a finite subcover of every open cover. And this every is really key here. You can't just take a set and make a finite cover of it and then say it's compact. You have to look at every possible open cover of that set until that they all contain a finite subcover. So an example of a compact set, if we just took X to be any finite collection of points, x1 to xn, and we take ui to be any completely generic open cover of X. Well, we know that X is contained in the union of all these UIs. Therefore, for each point in the set xj, it's contained within one, or at least one, of these I said I sub j here. This I sub j just means that this is whatever I index happens to contain the point xj. And again, there could be more than one. For example, if we had a point in here, then U3 and U4 would both contain that point. We only, for this proof, you only need to just choose one of them. Because each point can only be, has to be contained in at least one of these sets, because X is fully contained within the union of all of these, then we can just take those n sets, I1, I2, up to In, and X is contained within that union, because each one of the points within it are contained within. So X1 is contained within here, X2 within here, Xn within here. So you just take their union, and because X is finite, then that should be contained within this union here. So no matter, so we have no sort of specifications on this open cover. It's completely generic. It could very well be infinite, but no matter how tricky this is, we'll always be able to find some finite subcover. So a drawing of this example, if we had this sort of collection of sets, U1, U2, U3, U4, and then it sort of, however the set is constructed, it starts big here and translates a little bit and shrinks, and again, keeps going smaller and smaller. And if we had the finite points, number of points x1, x2, x3, and x4, well, we can see that x1 is contained within U2, x2 within U3, x3 within U3, and x4 within U2. So these are our open sets, as in here. So that means we can just count, because this would be U1 down to, U infinity, if you like. This just keeps going on forever. But we only actually need to take, in this case, two of these open sets, and this forms an open cover because each of these is open and X is contained within their union. So this would be just one example of an open cover of the collection of points X, and the finite subcover that we could create from that. Here we've shown it exists in complete generality, and here we've just shown just one possible way that could look. So an example of something which is not compact is R, the real line. So you might be tempted to think, well, R is a subset of minus infinity to 1 union minus 1 to infinity. Each of these is open in R, and there's a finite number of them, and R is contained within their union. And you'd be right saying that this is a finite open cover of R. But again, the definition of compactness says that you have to look at every possible open cover of, in this case, R, so that they all have a finite subcover. So if we look at this formula for constructing open sets, UN is minus n to n, the interval. So U1 is here, U2, U3. Well, we can see just from this drawing that U1 is contained within U2, is contained within U3, and so on and so forth. And if this process goes on forever, if we just send the limit of this as n goes to infinity, well, then we can see that R is definitely contained within the union. So in this case, our index set I is just the natural numbers. So in this case, this is an infinite cover because the natural numbers are infinite. So this will just go on and on forever. And because this contains, you can like this, if you like this is like, n equals 1 to some large m, un, and then the limit of m goes to infinity. And that will be this open cover here, which is infinite. So if there was a finite subcover of this open cover here, then because they're all nested, that means we should just be able to truncate it at some large n in natural numbers, and then that'll be it. That will be the finite subcover, because it would be subcover in the sense that it's finitely many, it's just a subset of these, and then finite, and then we're truncating it for some n. That means that R will be contained within U1, union, all the way up to UN, but because they're all nested, this is just equal to UN, which is of the form minus n to n, that means that R is contained within minus n to n, which is of course not true. And this is a symbol for a contradiction. So that means that R is not compact. We've shown that there exists at least one open cover of R here, which does not contain a finite subcover because we cannot just stop after n elements. Now, it's not always the case of you just taking the first n and that will provide a finite subcover. That only works in this case because we've nested them. So we can now look at this result here, which is very famous and links back to what I said, where in RD, compactness has a very equivalent definition, which is that if X is compact, that is completely equivalent to it being closed and bounded, but only in RD. It's called the Hein-Borel theorem, and metric spaces which have this property are said to have the Hein-Borel property. So this just makes it a very easy way to, in your mind, figure out if something is closed or bounded for all the sets you'll ever cover in real analysis. So for example, we can show that since R is closed but not bounded, that was an even easier way to see that R wasn't compact. Here we have that this interval here, 0 to 1, is bounded but not closed. Therefore, it's also not compact, and there's an easy way to show this as well without using Hein-Borel. If we took un to be this interval here, 1 over n to 1, again they nest like how we did before, and this is kind of a nice way, a nice kind of strategy for looking to find open covers with no finite subcover. Because we can look at the limit as n goes to infinity, and we can see that this will approach indeed our interval. So that means that the interval is contained within the union over the entirety of the natural numbers of un, but there does not exist some finite n in the natural numbers such that we can truncate this union after that n. Because they're nested, this union is just equal to un. So 0 to 1 will have to be contained within un, which is just 1 over n to 1. And for any natural number n, this cannot be true. So 0, 1, the open interval is not compact, but that is also just given by Hein-Borel. Now we have that here, continuous maps preserve compactness, which is not a very intuitive property without Hein-Borel. This is normally actually kind of given first in our real analysis course, and then this is given second. So to sort of give the idea of it, if we had an open cover of the image of X, right, then we can look at the pre-image of that, and so that X is contained within the pre-image. So that's the pre-image of the union. So that X is contained within the union of the pre-images. Because f is continuous, that means that each one of these sets here, f, this pre-image of ui is open because ui is open, and continuous maps the pre-images of a continuous map of an open set will be open. So it means that each one of these here is open. That means since this is an open cover of X now, then it has a finite subcover because X is compact. So we can just take some uik, where k goes from 1 to some finite n, and X is contained fully within that. And now switch back to images. So just look at the image of both sides, and then we can just bring this f inside here and cancel it out. Just get that the image is contained within this open cover here, and this is finite as well. So for any open cover of the image, we have found a finite subcover, so the image is compact. This is a very important result as well, which is often used as an easier way to deal with uniform continuity. So if X is compact and f maps X to Rb and f is continuous, that means that f is uniformly continuous. Now this really, at least wasn't obvious to me, so I think it's definitely worth going through the proof. If we let any epsilon greater than 0 be given, uh, we want, so for uniform continuity, we want just some completely global delta such that F will map balls of radius delta into balls of radius epsilon, both centered on x and then f of x, respectively. So for any x in our set, there exists some radius here, delta x, such that the balls centered on x of radius delta x are contained within f of x, so balls centered on f of x radius epsilon over 2, and epsilon over 2 is just that later we're going to get, you can see here, we're going to add to them together. So this is just the definition of continuity. So each one of these balls forms an open cover of x, and in fact we can just take the radius to delta x over 2, and that'll also become hopefully obvious in a second as to why we've done that. But that this will make sense because, so here we have x as our indexing set. So if x is, you know, even some interval, this won't be finite. So this is what I was saying earlier about that indexing set I can be any way to kind of collect all the points within a set. So if it's like around every single possible point, we're just drawing a small ball around it and taking the union of all of those. And of course, that will cover the whole set. So because this is an open cover of x and x is compact, there exists a finite subcover. So we can just take I going from 1 to n and now subscript these with i's here. So because it's a finite set, and there's a finite collection of these delta xi's over 2's, we can take the minimum of it. So the minimum of a finite set will always exist. So just look at finitely many of them and find the smallest one. So let that be our delta, and I claim this is going to be the global delta that works. So let's just call that just delta xj over 2 for some j. So I'm claiming that this works. If we have any 2 points that lie within this global delta, then they'll be mapped within an epsilon of each other. So again, balls, sorry, not necessarily balls actually, just any points that are close enough here within a delta will be close enough within an epsilon under the map. So if you just look at any 2 points, z and y, that are within that delta, just pick some I which z is contained in, because z must be contained within at least one set of these forms, because those sets form a cover of our set x, and z belongs to x. Then I claim that y must be contained within the ball centered on the same point of twice the radius. So if we look at any point, the distance between any point y and the center of the ball xi here, well, we have the triangle inequality employed here. So look at the distance between, this is necessarily, sorry, this is less than or equal to the distance between y and z plus the distance between center of the ball and z. Well, center of the ball and z we know are necessarily strictly within an delta xi over 2 of each other, and you know that y and z are within a delta of each other, and delta is the minimum of all of these sets. So that means that this will necessarily be strictly less than delta xi over 2, because either this I is this j, in which case this just equals delta and this inequality holds, or it's not equal to that j, so it could be larger than it, in which case this inequality also holds because it's just larger than that j, and it's definitely, sorry, than this delta, and it's definitely less than delta. So now we can probably see why we took over the deltas over 2, we add them together, And that means that these points x, y, and xi lie within delta xi of each other, which means that both y and z lie within that ball because, of course, this ball which z is contained in is just a subset of this larger ball, and we've just proved that y is within that ball. So from this, we can show that if any two points z and y are within a delta of each other, we can look at f of that z and f of that y, which again, we can look at the triangle inequality. So we look at the distance between f of z and f of xi and f of y and f of xi. And because they both lie within this specially constructed ball, which have these properties here, that means that each of these will be within an epsilon over 2 of each other, and this is why we just epsilon over 2, we just add them together to get epsilon. So that means that the image of these points will be within an epsilon of each other, so long as the points themselves were within a delta of each other. And that is the definition of uniform continuity, that you sort of have this global delta that works for any two points that are close enough in the domain will be mapped within any given epsilon of each other in the codomain.